Welcome back, design junkies, to Mechanical Engineering Made Simple.
Hello again.
Today we are doing a deep dive that connects the absolute smallest imperfections in a part to, well, catastrophic failure. We're talking fire and brimstone.
That's a good way to put it. We're looking at the microscopic battle happening inside basically every spinning machine you can think of. Specifically, why critical parts like bearings fail.
And it comes down to the twin demons of heat and vibration.
Always. And we've got a whole stack of sources here.
We do everything from hydraulic installation manuals to the deep, dark arts of geometric dimensioning and tolerancing, or GD&T.
And our mission really is to connect those two worlds, to
Yeah.
show how the physics of failure, fluid dynamics, torsional shake, is directly prevented by the language engineers use.
Tolerances and fits.
Exactly. It's the language of precision. You can't solve the problem if you can't speak the language.
So let's start where the failure so often begins, the installation. I was stunned to see how often it goes wrong right at the start with dry mounting.
It's so counterintuitive, isn't it? You'd think less lubrication means a better grip, but that is precisely the wrong way to think about it.
So what actually happens?
Well, the sources are very clear. Avoid dry mating surfaces. If you try to mount that bearing dry, the friction is just immense.
And it damages the surface.
Instantly. You get what's called micro-smearing on the shaft and the inner ring.
But the real kicker is what that friction does to your setup readings.
Oh, absolutely. That insane friction means your hydraulic pump shows the required pressure way, way before the bearing is actually in its correct starting position.
So the operator thinks they're there, they've hit their number.
They think the job's done.
Yeah.
But all they've done is fight dry friction. It's a completely false sense of security.
Okay, so then what about this? This idea that a bearing might actually move down the tapered seat after you've released the hydraulic pressure, that seems backward.
It does, but it makes perfect sense when you think about what failed. The whole point of the drive-up is to secure the bearing and reduce that internal clearance. If the bearing slips back down after you release the pressure, it means the oil film, the very thing that should be holding it, has squeezed out.
So the initial dry mounting damaged the surfaces so badly that they can't maintain that final secure oil layer.
You've got it. The initial damage compromises the final grip. The bearing is essentially trying to reseat itself later, probably during operation, which is a disaster waiting to happen.
And speaking of the procedure, that hydraulic nut seems to have its own failure modes. Why is it so important to tighten it against the bearing before you even start?
That's a pure safety measure. It's there to prevent blowing out the piston seals.
How so?
If you don't snug it up first, the piston inside the nut can move too far axially before it even starts pushing the bearing. And if it moves too far, during that final high-pressure push, the seals can literally be forced right out of the nut.
And then you've got a catastrophic loss of pressure.
You lose the tool, you could have an injury. It's a tiny procedural detail with just massive consequences.
It really is. And for really big bearings, the setup tools themselves can be a problem.
Yeah, that's something people overlook. The drive-up distance can be huge. You, as the engineer, have to check if your dial indicator can even measure that far.
So if the drive up is, say, 13 millimeters, but your indicator only goes to 10.
You're in trouble. You have to plan for that, maybe add extension rods. If you hit the indicator's limit halfway through, you've lost your measurement data. You have to start over.
So assuming we get past the installation, the next fight is against the dynamic forces, vibration and shock.
Exactly. We're moving from the static world into the much more violent world of continuous motion and resonance.
This is where things can really tear themselves apart.
Oh, yeah. For any complex rotating machine, an engine, a turbine, torsional vibration is just a killer. And managing it is incredibly technical.
The sources get into this fixed point method for tuning a damper. What are those points A and B on a resonance curve actually telling us?
Right, so this is all about tuning out dangerous harmonic energy before the machine shakes itself to bits. The fixed point method is how you do it reliably. Those points, A and B, are two frequencies on the curve where the amplitude doesn't change no matter how much damping you have in the system.
So they're like stable anchors in the data, even if the damper itself is changing.
Precisely. They are mathematically stable. So the procedure is you adjust the damper spring constant until the vibration spikes. The amplitudes at points A and B are the same height.
And when they're equal, you're optimized.
You're optimized. But if that resulting amplitude is still too high, well, that tells you something fundamental.
The damper is just too small for the job.
Exactly. You can't tune your way out of it. You have to go back and calculate for a bigger damper. It proves this isn't guesswork. It's a very precise science.
And that kind of precision is critical because engineers are always making trade-offs. It's not just about performance.
Not at all. This is where theory crashes into reality. You might prefer a low-cost, weaker material over a super expensive, strong one, but only if you can prove your design keeps the stresses low.
You're balancing cost, schedule, safety.
All of it. And you can't ever compromise on safety, but that cost pressure is always, always there.
Those choices really matter in a high-vibration environment. One of the biggest warnings in the material was about using rivets.
Yes, specifically cold-driven rivets. The sources say they are completely unsuitable for any structure that's going to see shock and vibration.
Why is that?
Because when you drive a rivet cold, you lock in a huge amount of residual stress.
Creating a weak point.
A perfect focal point for a crack to start the second that assembly begins to shake. If it's going to vibrate, the rule is simple. The rivets have to be driven hot.
It's all about the installation technique, not just the part itself.
Which brings us to the real power tool for fighting these rhythmic forces. Damping.
Apply damping treatments.
A powerful design tool. It's how you directly reduce the maximum stress from those periodic, repeating vibrations.
And the math behind it is surprisingly simple, isn't it?
It really is. The maximum stress in the structure is just inversely proportional to its damping ratio.
So double the damping, you have the stress.
Simple as that. It's a direct intervention. That's why you see all those complex pads and special materials in high-end equipment.
Okay, so we've seen how things fail. Bad mounting, blown seals, constant vibration. Now let's get into how we prevent it from the start, using the formal language of GD&T.
Right. This is how design intent actually makes it onto a physical part. And it all starts with the system of standard tolerance grades.
Which is what makes everything interchangeable.
Exactly. It's a brilliant system because it ensures that a certain grade represents about the same level of manufacturing difficulty, no matter the size of the part. A designer in one country can specify a fit, and a machine shop on the other side of the world knows exactly what that means.
And that lets us define different fits. Everything from a loose running fit for a piston rod to a super tight interference fit.
A force fit, where you literally have to heat one part and freeze the other to get them to assemble. The choice dictates the entire function.
Okay, so let's get into the heart of GD&T. The foundational concept is the feature.
Which is really just any physical portion of a part. A hole, a pin, a flat surface, a slot.
And from that, we get the feature axis.
Which is the axis of the, and this is key, the unrelated actual mating envelope.
Why that specific, very technical definition? Why not just the center of the hole as you made it?
Because the as-built hole might be a little bit out of round or wavy. The mating envelope is the theoretically perfect cylinder that would just touch the highest points of that real feature.
Ah, so it creates a stable, perfect reference axis, no matter the small flaws in the part itself.
Exactly. It's repeatable. That's the key to making millions of interchangeable parts that all fit together perfectly.
Okay, let's tackle a big one. Least material condition, or LMC. When and why would a designer use that?
LMC is your tool when the most important thing is guaranteeing a minimum distance between features.
So like minimum wall thickness, you're protecting the part from breaking.
You are protecting its structural integrity. And here's the clever part, the part that machinists love. As the feature departs from its LMC size, which means you're adding more material, making the wall thicker,
You get a bonus.
you get an equal increase, a tolerance bonus, in its positional tolerance. The part becomes easier to make, but you've still guaranteed that minimum strength. It's an elegant trade-off.
That's fascinating. What about a fundamental shape, like flatness? There's a tricky relationship there with the size tolerance.
Right. The flatness tolerance is basically two parallel planes the surface has to live between. And normally the rule is your flatness tolerance has to be less than your size tolerance.
You can't be flatter than the box you're allowed to be in.
Pretty much. But there is one symbol that changes everything. The independency symbol.
The free pass.
I like that. The free pass. If a designer applies that symbol to the size dimension, it breaks the link. The requirement for perfect form at maximum material condition is gone.
And the flatness tolerance can actually be larger than the size tolerance.
It can. It gives the shop floor a lot more freedom, but it completely changes the tolerance analysis for the designer. It's a big risk-reward calculation.
So let's bring this all back to our bearings, to rotating parts. To stop that heat and vibration, we need perfect alignment, or coaxiality.
It is absolutely essential for durability. If you have a shaft with multiple diameters, they all have to be perfectly on the same center line, and we control that with positional tolerance.
At MMC, LMC, or RFS?
depending on what you need. And the data modifier you choose is critical, especially the maximum material boundary, or MMB.
What does MMB do for the machinist?
It gives them a bonus. If the datum feature itself departs from its MMB size, it creates extra allowable wiggle room or displacement between its axis and the axis of the feature you're controlling,
So it loosens the alignment requirement just a little, making it easier to machine.
without compromising the function when the parts are at their worst-case material size.
Okay, so to check the actual rotational quality, we move to run-out tolerance.
Yes, runout is the master control for anything that spins. It's critical for killing vibration before it starts.
So how does it work?
You take circular runout, for example. You rotate the part around its datum axis, and you measure at different points along the surface. And that one measurement controls the combined cumulative variations of both circularity and coaxiality.
So it's super efficient. It catches multiple potential errors in one go.
Incredibly efficient. It's how you guarantee that component will spin smoothly and keep those dangerous vibrations from ever getting a foothold.
And on a complex modern part, you might not have just one reference frame.
Not at all. It's common to have multiple datum reference frames on a single part. One side might need to align with a housing. Another needs to be coaxial with a completely different shaft.
And the key is you have to define the relationship between those frames.
You absolutely must. If you don't explicitly dimension the relationship between your reference frames, the design intent breaks down. The communication fails, and the whole assembly fails.
So we started this deep dive with the triggers for failure, dry mounting, blown seals, vibration stress, and we've ended up with the language of prevention. GD&T, LMC, runout.
The connection is so direct. Solving a huge system-level problem like tuning a torsional damper with that fixed-point method we talked about. It all comes back to being able to communicate and enforce these geometric specs with just unwavering precision on the drawing.
Precision is the foundation.
It's everything in mechanical reliability.
And that brings us to our final provocative thought. It connects geometry, materials, and scale. Our sources point out that the rupture factor for brittle materials varies inversely with the absolute scale.
Which is a fascinating and slightly scary concept. It means as you shrink a part down, its ability to handle stress concentrations doesn't shrink with it. In fact, the problem gets worse.
So if you're designing a very small part with sharp corners or holes, you need to pay disproportionately more attention to the material strength than you would for a larger version of the same part.
That's exactly it. The smaller the component, the more unforgiving the material demands become. Something for you to all mull over until our next deep dive.